telling us about AdS Virasoro-Shapiro dispersive symbol. Go ahead.
Thank you, Vasco, for this introduction. So here's the title of my talk. It's AdS Virasoro-Shapiro from dispersive sum rules. It's based on a paper that we made with Fernando Alday and with Tobias Hansen. So our paper will be about n equals 4 supreme mills in the pointer limit. So let me start by reminding you about the flat space Virasoro-Shapiro amplitude. This nice function, which is a product of a ratio of gamma functions. And so this function has some properties that we know. So it is 3-level scattering amplitude, it's crossing symmetric, it involves infinite exchanges, it is unitary, and it is polynomially bounded. So I will show you a similar quantity in AdS, so a quantity that has similar properties. And this scattering amplitude has this low energy expansion. So when you expand in powers of ft and u, this is the way to do it, and you encounter these zeta values. This will be interesting for us because in AdS something similar occurs, okay? Good. So let me tell you what is this AdS Virasoro-Shapiro amplitude. So we'll consider a four-point function of all tools, which are superprimaries in the same multiplet as the stress tensor. And this four-point function can be written as in terms of just one non-trivial function of the cross ratios. So big U and big V will be the usual conformal cross ratios. And we will study this four-point function using Malin amplitudes. Okay? So here's the Malin representation. And so in Malin space, you do not have Mandelstam variables, you have Malin variables, and these Malin variables are dimensionless. So they are different from Mandelstam variables in this sense. But here the point is that this Malin amplitude has properties that are similar to a three-level scattering amplitude. So now let's just change the definition. Okay, so we write the four-point function as an integral, and there's a non-trivial function which is called a Malin amplitude. Okay? So our talk will be about this Malin amplitude. Okay? And there is a variable u, which I introduced, which is 4 minus s minus t. Okay, so let me tell you some properties of this Malin amplitude. And for the moment, we will think in the pointer limit, and we will think at finite lambda. So at finite of coupling. So the Malin amplitude is crossing symmetric. It's Malin amplitude that I wrote. So MST is MTS, which is M as a function of S and U. And it's also a metamorphic function, so suppose I consider the OPE, let's say I consider the OPE in the S channel, and suppose I take the single channel, and suppose there's some superprimary exchange of twist down spin L, then the following happens. Then the Malin amplitude has a series of poles, there's a sequence of poles, in this way. Okay, so this is what happens. And this is similar to a scattering amplitude, but now we have many poles. We do not have just one pole. In scattering amplitudes, you have one pole for each part. And instead of having Gegenbaum polynomials, you have some other polynomials. These are called Mach polynomials. The point of our Mach polynomial is that we know them. It's like conformal blocks. And this residue comes proportional to the OP coefficient, which is this c squared. And so unitarity is just a statement that c squared is positive. the other thing I want to say, is that this now inevitable is polynomially bounded in the following way. And P. And this is because of the bound case. Okay? So the situation is very similar to the one in scattering elements. Real part of P is smaller than 2. Here we are taking T fixed.
Can I ask a question?
Sure.
So since your integral representation is done symmetrically in SIP, how do you get the crossing symmetry?
Because I didn't have the crossing symmetries in P.
So what is the basic formulation of crossing symmetry of T?
It's such that this equation is true. I think it's just TUV, TVU,
No,
T.
because the power interface of U and V are different.
I think there is one U goes to V, but there is a prefactor in the correlator. So it's U squared times GUV is equal to V squared, sorry, the opposite. V squared GUV is equal to U squared.
But usually that prefactor depends on the string dimension of
I mean, we wrote
That's
this
correct.
What am I saying?
So sorry, so this is a 2. So when he writes O2, 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 so this is a operator of dimension 2. Indeed, you're right. And then there is another one that sends UV to 1 over UV over U. And this is the third one.
Wait, this thing that you write is the reduced
Yeah.
focal function. So when you cross it, there is also an extra piece inside the free theory.
True. But since it's like free theory, we don't want to manually transform it. So the logic is, as I said,
Okay.
the 4-point function has a part which is easy, which is the free part, and the part which is the reduced correlator, which involves the unprotected operators, which is the non-trivial part. This is the part that we want to manually transform. And then when we analyze crossing, we take all these things into account and very careful. And then this is the end. Actually, no, we took this from a paper. Perfect paper. So they were careful. They understood.
Question? This formalism applies to any operator? Doesn't have to be the stress tensor?
That applies to any break. Good. So ideally, we want to aim at studying the Marin amplitude at finite coupling, but this is of course extremely hard. And in particular, in AdS, trajectories are not linear, like in flat space. So we will not study the Marin amplitude at finite coupling. What we will do is study it at strong coupling. And what we would like to aim at is, I don't know if you guys remember, there was this formula for the scattering amplitude for the low energy expansion. There was an expansion in terms of zeta values.
Sorry, João, can you just remind me this bound or this polynomial bound on M? So this is along any complex direction. This has been proven or
This
an
has,
assumption?
this has been proven here in this regime. Then you might wonder when you take
What is that regime? S goes to what?
S goes to I infinity.
I.
And the real part of T is fixed, but you suppose going, for example, in this direction. And yeah, there could be. When I use the dispersion relation, I will need a little more than this, but this is pretty standard.
So this is true for finite lambda. In
This is
order
true.
by order in large lambda, the word behavior gets worse and worse.
That's true. Yeah. Of course, we'll be careful with this.
One question, sorry?
Non-perturbative is easier to understand because it would be just saying that the Lorentzian correlator is bounded by the Euclidean correlator, but that margin you cannot make the same argument because there can be logs. But then you need to use this model.
Sorry, the intermediate operators in the OPE, they have some particular specific form in this case? Is that
So they have twist tau, my tau is absolute, twist tau and spin out.
SPNL? And but in the denominator?
In the denominator, so S was a Mellin variable, so denominator you have S minus tau minus 2m.
Sorry, and the formula on the right applies in which is it a
This formula.
yeah.
This formula will not exist. This is just something written on the board at this point. Okay. Any further question?
Yeah, sorry.
Please.
So we distinguish the 2 from the tau because of the
the 2 from the tau. So this is a 2, this is a tau. It's
Okay.
gonna be a
So,
constant t.
so it's the little circle.
How to just do it, stop. How to do it.
Used to have these problems in primary school. I don't know if you guys know, in Portuguese primary schools back in my day, teachers could hit students.
Teachers could.
That's true. I'm not lying. But I was never hit. Because I was a good student.
Students hate teachers.
So this is in secondary school.
It's really crowded.
Okay, so let me tell you about this strong coupling expansion that we want to study. And let me introduce two polynomials, sigma 2 and sigma 3. So sigma 2 is this and sigma 3 is that. And then the Marin amplitude has the following expansion. A over S minus 2. Okay, and so the line has this expansion at large lambda, and this pole is just comes from supergravity, and these 1 over lambda corrections are so-called stringy corrections. And so this is what our paper is about. It's about studying these stringy corrections. Okay? Stringy corrections. So, and this is, by the way, so this works a little different from a scattering amplitude. So in a scattering amplitude, you cannot add two Mandelstam polynomials of different degrees because these are dimension full quantities. But in here we have dimension-less quantities, so you can do that. So in here you have sigma 2 times some number plus 1, and this is legal. Good. So I want to tell you what you people know about these stringy corrections. Okay? So before talking about the So first, let me reorganize these stringy corrections in a certain way. So take this expansion, and now let's look at this formula, and that expansion can be written this way. So let's convince ourselves of that. So if whenever you have a polynomial sigma 2 to the power a, sigma 3 to the power b that appears, you consider the first lambda, the first power of lambda with which it appears, it's this power. And then you consider this coefficient, you call it alpha. And then you can consider a correction, then you will call it beta, and so on. So it's convenient for us to write things in this way.
So sum goes to positive infinity?
Sum, this one.
Yeah.
That's an infinity, yeah.
Okay.
These things are unambiguously defined.
They are ambiguously different.
But
This is the way
you have to justify why, like at order 1 over lambda to 3 halves, you don't have some sigmas. You have to justify why.
It's by
Yeah, you have
consistency.
to explain.
Thank you.
Otherwise,
It's by consistency with what's specific.
Yeah.
So.
So you're not really using this function because this term in this upcoming expansion, each of these terms flows out for large S.
Indeed, not yet. So my talk will be about exploring how can this bound be consistent with this. So right now this is just okay. So let me move on. So we wrote down this formula, and so what do people know about these stringy corrections? People know these alphas. They come from the spot space limit, so people know all the alphas. And then from localization, people know a few more numbers. So turns out that localization will give you two linear constraints at each ordering 1 over lambda. This localization gives So in practice, people know this number, people know these two numbers, and people know the next order. But then when you consider the order after that, there are 4 numbers, and so people don't know. Okay? And here are the numbers, the other numbers that people know. So people know beta, 0, 0 is 0, gamma 0, 0 is this. So this is a zeta. And then zeta 1, 0. Okay, so these are the numbers that people know. Good. So this is what we know.
Sorry, what's gamma and
Gamma. There is no gamma. Because it's like alphabet, and then the next one is gamma, the next one is delta. Okay, so this is the review part. So now we want to study this memory amplitude, and we will do it using dispersion relation. So let's first think about this at finite number. Okay?
You have more space that you could write maybe plus gamma over lambda, just to...
No, please don't cross that.
Oh,
line.
The gamma.
sorry.
Okay, so let's use dispersion relation. And so we write, it's convenient for us to introduce a subtraction for reasons that will be clear later. So let me just introduce it. This is a product from I equals 1 to q, s minus 2 minus 2i, p minus 2 minus 2i. Okay? And this q is a non-negative integer. So we consider this object and we consider this object, and now we want to write a dispersion relation for it. So we write it as an integral around the point, and then we blow this object to infinity. So let's write something like this. And then the arc at infinity vanishes, and then you pick up other poles, which are the physical poles. And there are 2 sequences of such poles. This sequence and that sequence. And so here the poles are at tau plus 2m, and here the poles are at 4 minus u minus tau minus 2m. Which, so I'm taking this dispersion relation, I'm thinking of this dispersion relation with a variable u fixed, so we pick up the poles in 2 channels, in the S channel and in the T channel. Okay? Good. And so, we have understood, we saw before how to take residues of the memory amplitude, and so it must be that this thing can be written as sum as the following. So I will now introduce a functional, and this functional depends on the Mach polynomials. I don't want to write down the functional explicitly, that's very important. So it's clear that we get this an equation like this, and this omega comes from the residues of the memory amplitude, okay? And so let me tell you some properties of this function. So it's a dispersive functional in the sense that it vanishes for double traces. So in this theory, the double traces, they have twists. Tau equals 4 plus 2n. And then there can be corrections in the lower C, which are the enormous dimensions. And so turns out that this omega, when you evaluate it there, it just vanishes. And then the structure of zeros is important. So whether it's a single zero or it's a double zero, this is very important. And this depends on these q's. So, and the equation is tau omega tau. So the derivative vanishes for the tangent trajectories which have n big, and it's not does not match. Okay, so we derive this equation of finite number. And now we want to take lambda huge. So now suppose that lambda is a huge number, it's a million or 10 million, it's a very big number. And then the left-hand side of this equation, so now we are always thinking, so during the talk we will always be thinking about this equation. At strong coupling, the left-hand side of this equation is very well approximated by the strong coupling expansion. So it can be expanded in 1 over lambda. So it must be that on the right-hand side, we'll put operators, and their conformal data must organize itself in such a way that this equation is true. So it must be that conformal data can be expanded in 1 over lambda. Well, this is well known. But in such a way that this equation is true. Okay? So this is an equation that we want to explore.
This is when you use the bound.
We use the bound to establish the equation. Good. So on the left hand side, we'll just put these stringy corrections, and in principle, we don't know them. And on the right hand side, let's think about the operators that are exchanged. So the obvious ones are the low energy operators, so operators that have small twist. For example, some of them are the short multiplets, so operators that have protected dimensions. And basically about these, everything is known about them, they have been tabled, so we can just take them, feed them into some rules, and evaluate the result, and that's it.
Sorry, João, can you explain where the poles on the left come from? Because the ones on the right are from the Manin amplitude, and the ones on the left are?
They are also from the Manin amplitude.
Where are they shifted up?
Because they depend on U, and U is the complex variable.
That's a U, okay.
That's a U. It's 4 minus U minus tau minus 2.
Sorry, and on the right hand side, where are the poles?
You see, you mean in this equation?
Yeah.
So the logic, let me repeat the logic. So you have this function, right? And now you can write this function using Cauchy's theorem on an arbitrary point as an integral around this point. And then you can blow the contour to infinity due to that bound that I wrote. And when you do that, you pick a poles. All the poles of this function. And so you pick, and now I'm listing them. It's these poles and it's these poles. And when you do that, you evaluate the residue and you want this equation.
So are you drawing the S-plane of the
I'm
integral?
drawing the S-plane. This is very important.
So somehow that infinite sum becomes, blows up near the poles. Is that how I should think about it?
This infinite sum will blow up near these poles.
Did you pick up the subtraction and the things that you were developing?
It's an excellent question. You don't due to the poet of conditions. So this Marin amplitude has zeros because you have gamma in the definition. The definition of the Marin representation, there's some gamma functions, they have double poles, so the Marin amplitude must have zeros to
This
cancel
is
that.
S minus tau minus 2y. Is it the thing that you're dividing by?
The pole is at tau plus 2n.
No, the thing that you're dividing by is what?
S minus 2 minus 2i. Okay, ask if you don't understand my handwriting. And this is t minus 2 minus 2i.
Sorry, but if the subtraction is of high enough degree, then you don't have enough zeros, right?
No, we have enough zeros.
You have enough zeros?
Yes. Because these are always at the double trace location.
Right, but if I have a triple pole, then do I have a triple zero in the numerator?
You do not have a triple pole.
Ah, okay.
Good. So let's continue. So we have this equation. Left hand side we put the string corrections. Right hand side we put the operators. About some of these we know everything. So I'll just go over here and then they're pretty well. And there are some that we also know. These are called the double trace operators, which we know, so we can compute their enormous dimensions from the stringy corrections. Even though we don't know them, the enormous dimensions will come as a function of just one number. Okay? And now, crucially, we have access to another set of operators, which we call string operators. And these are operators whose dimensions grow with lambda to the power of a quarter, and so among them is the Cauchy operator. So let's think for a moment, why do we have access to these operators? So people have been using the analytic Bootstrap for a while, and people have been studying contact interactions in AdS, which is what we're doing. In particular, my supervisor, to my knowledge, was played a key role in this one, who apparently did not come to the talk. You will be listening, I think.
Did he hit you?
Now, during my PhD, it was rough. We study these things non-perturbative. Now we are in the point of agreement. It's much easier. It is what it is. Okay, so what João and his collaborators, there's this famous paper, HPPS, and so they studied these contact diagrams and they studied the conformal block expansion. And they noticed that you just need double traces to study them. So you can reproduce them using double trace operators. So how can it be that we have access to these operators? Because we are not doing a conformal block expansion. We are expanding in 2 channels, so it's a different expansion, and it turns out that you need other operators. This becomes clear if you think in terms of the dispersion relation. So if you have a contact diagram which has a very high degree, suppose you put sigma 2 to the power 20, and I put, I don't know, q equals 1, then this contact diagram will not obey this dispersion relation. So there will be arcs at infinity, one must take them into account. Okay, and so the moral of the story is that we have access to these operators. And so our talk will be about studying the interplay between these operators and the stringy corrections. Good. So now I want to mention the punchline of our talk, but before doing that, there's an auxiliary result that I need to describe. So it's 10, right? I'm bringing 10, right? Okay, so now I want to skip to the results. So I want to go to the results, so I will skip some manipulations. From the dispersive sum rules, it comes out the following. So let's input that these string operators, their dimension at leading order in the coupling goes with number to the power of quarter. We input that. But we do not input this number, and we do not input these OP coefficients. So if we know that these operators, they grow like this, then the dispersive sum rules will tell us what is tau 0, and they will also tell us what are the OP coefficients. So the OP coefficients are like this, and where tau is this twist, and there's a function f, and this function f starts at 1 to the 0. Is this formula clear? Since 2 to the power minus 2 tau, tau 2 is 6, sine squared by tau over 2. Okay, so I want to tell you about this data of the string operators. And now, for the main result. So the main result is that we establish equations that will connect each string correction, with the data of the string operators.
Then these OP coefficients, they go what?
This side square.
Yes.
It has to do with the level crossing. So it's when double trace is crossing single trace operators, and OP coefficients are expected to go up. We had a discussion about this last week.
So basically, what happens is that you have the dimension of a heavy operator, it becomes kind of an integer, so it agrees with the dimension of double trace operators or multi-trace operators of BPS. And that gives you a mixing that in principle you would need to resolve, but we are not resolving that, and because of that, there is this prefactor.
Thank you for the better
Sorry, can I
explanation.
maybe it's a bit stupid. So the thing you brought, this C square, this OP coefficient, is it just a way to parameterize it, or there is some non-trivial content?
There is no trivial content because I'm saying that the OP coefficient grows. Well, for example, I'm saying that it decays exponentially at infinity, so this is not trivial.
So are these Fs, they cannot depend on tau, they just number.
That, yeah, so they grow in that way. Okay, so what's the structure of the equations? the equations have the first equations are nice and they have the following structure. So the easiest of the string corrections, which are the alphas, they are related to these operators at leading order. So they are related to tau 0 and to f0. So to the twist and to the OP coefficient at leading order. And then the equation for beta involves the same f in tau 0, but also f2 and tau 2, which is the next correction. And so on. And so then this is the trace. So now, for if I wrote gamma, it would involve f4 tau 4, and so on. So that's the way it is. Okay, so this is the main result that we have. So if people from interoperability tell us all this data, then we can compute these corrections. So now I want to analyze these equations, and I will show you the easiest of these equations, which is this one. So consider alpha A0, that's equal to a sum, and we sum over all these heavy operators, and this is just the equation that comes out of our sum list. F0 R and tau 0 R 6 plus 4A. Okay, so I'm introducing here some letter R. I just mean that these operators, well, they have quantum numbers.
What fixes F1 and tau 1 is?
At F1 tau 1 at the moment are not fixed, we will fix them though. So, this is a concept about how things scale with lambda.
No, but you're writing down now these equations.
Ah, right, why don't we have F1 tau 1?
Yes.
So in here the way this works is that the real, I expanded this in powers of 1 over lambda to the power of quarter. Really you should think about this as 1 over lambda to the power 1/2, because it's like alpha prime. And so the F1 and tau 1, they are not 0, but they will be very simple. But then F3 is 0, F5 is 0, F7 is 0, F9 is 0, tau 3 is 0, tau 5 is 0, tau 7 is 0. And so the structure of the equations is this one. You see, this tau 1 is basically a factor. Where is tau 1? This tau 1 enters here, because it enters here as a factor. So, similar to puzzle, but everything I said.
Could it be that there's a way to rewrite this, the c squared, the factor in front of f just comes from asymptotic expanding some factor? Or could it be that there's a different way of writing this factor, where you just don't have the both terms in the series of f?
Sounds possible. Yeah, probably. Yeah, it's just an asymptotic factor. Okay, good. So let's analyze this equation. First, let's make sure we understand every symbol. So we sum over all the operators, and that's R, because these operators, by R I mean corrected with a quantum number. They can be spin, and there will be a quantum number that we discover, and then there can be other quantum numbers, okay? So I just denote them by R. And this is tau 0 as a function of this R. This is 6 plus 4A. This is some factor, and this is F0s, okay? So this is the equation that we want to solve. So let's try to solve it carefully. So, just like this, we don't know the left-hand side, we don't know the right-hand side, so it's not very promising. So what we will do to solve this equation is that we will input the flat space Virasoro-Shapiro. That's what we will do. Input flat PS, and by inputting it, then I will tell you what is alpha, and then I'll solve for F0 and tau 0. Okay? So, then you go to the Virasoro-Shapiro amplitude, and you find that this alpha is just zeta, now we come to zeta, 3 plus 2a. Okay? So now we have this equation, zeta 3 plus 2a is equal to this. So now it turns out that it is good to look at the limit a goes to infinity. So let's look at the limit a goes to infinity. Because in this limit, this zeta simplifies. And then, so let me look at this limit, then you have 1 equals to this sum. And let's look at this right-hand side. So tau 0 and F0 are positive. So what dominates? Must be the minimal twist. The minimal twist dominates. And so we obtain that 1 is equal to divided by tau mean squared and this is 2 powers. 3 was 2a, sum, or mean, and then you have F0R. So I sum over the operators that have been moved. Okay? Because these are the ones that are more important when you take AB. Okay? The other ones have small contributions. And by the way, this limit A large, we only have access to it because we introduced the Q's. So this corresponds to taking Q to infinity. So this is pretty important. Okay, so now let's think about what this tau mean can be. It's just
Maybe something to say at this point is that it's funny that it's like the tail of these alphas is related to the heavy operators with the minimal twist.
Thank you.
So that's kind of the
That's
message.
common. Good. So let's proceed. So we have this equation. Let's think about this tau mean square. Suppose it's bigger than 4, then the right hand side vanishes. Suppose it's smaller than 4, then it goes up. So it must be that tau mean square is equal to 4, so tau mean is equal to 2. So we just derive this. And we also derive that these sums for our mean F0R, that is 1. So we derive this information, okay? And now we can push this idea further because the zeta, when A is big, goes to 1, but then there are corrections to this, and so we can keep pushing this idea. So, this zeta function has this expansion. Equals to A is 1 over 1 to the power 3 equals 2A plus 1 over 2 to the power 3 equals 2A plus 1 over 3 to the power 3 equals 2A plus and so on. Okay? And so we use the same procedure. And now if you think about it, you will notice that this tau 0 must be equal to 2 square root of delta, where this delta is a positive integer. And this is a result that was known in the early days of the SFT, so it was arrived 25 years ago. This paper by Bootstrap and Oracle. They were studying short strings in AdS. But here we derive from the Bootstrap, and we have access to p coefficients and to subleading corrections. Okay, so now we learned about the tau zeros.
João,
Please.
since so A here is a continuous variable in the zeta, is there no?
No, sorry, I should explain. A is this.
Yeah, I understand. But once you tell me that the zeta function of 3 plus 2A, I can treat it as a continuous variable in this equation.
That's okay.
So is there no some inverse Laplace transform that you could do to just get some over here in terms of, like, it looks on the right hand side, it looks like that appears exponentially. There's no integral transform you could apply to this equation.
Could be that there's a smarter way of deriving these equations. We just put limits.
The thing is that you know only the function in principle in the integers, and that could be different ways of analytically continuing.
But how are you sensitive to that in this equation anyway?
So the left hand side is not, but the equations we derive are.
Okay.
We thought about that. It's a very good idea. And at the end, the solution means that it is actually analytic on both sides. But but there may be like problems with analytic continuation because equations were derived for a integer.
I see. Thanks.
It's a good question.
So, this looks like a game you can play also in flat space, like this. You can relate the low energy expansion of the Virasoro-Shapiro to the sum of its polar string mode. Then you get some constraints over the coefficient of each string mode. Can you comment on, like, do you get more, do you get less, do you get exactly the same? What do you get?
I don't have a comment. That sounds like a good idea. I haven't thought about it.
But isn't this the way that Penedones and collaborators computed the F-zeros?
I don't think so. I think they're in AdS, they take flat space limits. So it's not the same.
Well, it's kind of the same, no? As your question.
Yeah.
Can you
Yeah, I'm just saying you can play exactly this game in pretty flat space. I mean, and people have played this game in the 70s.
Yeah, you can reach the flat space limit through AdS, and by matching, by playing, I think you can say what F0s are, no?
The F0s are related to particle complex. So there are big coefficients, so they're like particle complex.
Yeah.
As you know.
But here, I'm just trying to understand the game here. So you have all these sum rules which relate this sum over every spectrum to these zeta values.
Yeah.
Of all these sum rules. These sum rules do they completely determine the edge, or do they partially determine the edge? What exactly? I guess you're getting there, but how constraining are they?
So, if you know all the data about these operators, no, wait. If you know all the data about these operators, you determine the string corrections. And if you know all the string corrections, you also determine all the data about these operators. So they're completely constrained. That's the answer to your question. So, for example, I will show you a case in which we know all the string corrections, which are these alphas, and then this fully fixes the OP coefficient and the twisted leading order.
See, so you're saying that the low energy expansion of the list of all the alphas, so the low energy expansion of M2 completely determines the steady spectrum?
That's what I'm saying. Yeah.
Okay. So do you assume that the position of the spectrum, you determine the OP coefficient?
I didn't get what you said.
Now you also determine the position of the, do you just determine the OP coefficient, or you also determine the position of each?
We also determine the position because it's this tau 0
Uh-huh.
that I use.
The only caveat is that there could be mixing for higher radio trajectories. So what one determines is some average of taus, let's say.
Okay,
João,
please.
can I ask a simple question? How do you input the flat space, Virasoro-Shapiro? You take the limit on the left hand side and right hand side of this equation, and then you look at how this.
So this is an equation in CFT. Okay? And then the flat space limit comes from it's a technique that tells you what is this alpha. And then the rest is we don't touch.
The right hand side doesn't.
The rest we don't touch, and then we read off.
What about the scaling of the twist with lambda? Is this also, can this also be derived, or is it a mistake?
Yes, it can be derived. It's like having massive states in the UV with mass 1 over alpha prime. So that's what you expect. So we take 1 over alpha prime and now pass it to lambda.
No, this I understand, but I'm asking if you could derive that from a CFT perspective, that this completion has to have states whose twist scales in this way with lambda, given this low energy expansion.
I don't know how to do that. Seems to me that things would be consistent. Suppose that it's near some number. Seems to me that naively things would be consistent.
Yeah, I think this is kind of what we did in our gravity paper on the flat space. But you need to use more dispersion relation. You need to use distracted ones. Because they give you some rules for gravity. And in gravity somehow set what sets square root of lambda here is the ratio between the sample charge and these algorithms of corrections. So that's what sets the state. So there's some rule for gravity and there's some rule for these corrections. You can basically determine lambda. So the mass of the dimension of the operators has to scale like this.
That's a great point. Okay. So we examined carefully one equation for the alphas, and then, as you can imagine, we considered all equations. So we considered alpha A1, alpha A2, alpha A3. And so let me tell you what we derived. And it turns out that these operators lie on the following Regge trajectories. So, and the rule is the following. So suppose you have delta equals to 1, then you can only have operators with spin 0. If you have delta equals to 2, then you can have spin 0 and spin 2. If you have delta equals to 3, you can have spin 4, 2 and 0. And so on. So these are the selection rules. And so operators lie on Regge trajectories. And this is the leading Regge trajectory, this is the sub-leading Regge trajectory, and so on. This comes out of the dispersive sum. That must be this way. And the sum rules also determine the OP coefficients. So and UP coefficients turn out to obey some nice formulas. So I'll now spend a few minutes describing them to you. And then we'll probably finish. So I have 10 minutes, am I correct? I have 20 minutes. What's the status? 10 minutes? 15. 15. Should I show this? Let's show this. Okay. So let's study OP coefficients. So we introduce some functions which we call nested sums. These nested sums are defined like this. We introduce them. The OP coefficients come out of nested sums like this. Here we have z and s2. And this one. This is the definition. And then z at n. And then z at s1. Above 0 is equal to 0. Okay? And from these nested sums, you can construct so-called multi-zeta values, which are generalizations of just normal zeta values. So you set these guys, and then you get a zeta, s, s1. Okay, so now what's the formula for the OP coefficients? So let me introduce some object that will capture the OP coefficients. So the sum and then you have L minus M plus 1, and then you have M, and then you have L plus 1, M, and then you have FC. Okay, so this contains the OP coefficients. Is the formula clear? And then the formula is F and delta 2 to the power n plus 1 gamma delta n, and then these W's obey recursion relations in terms of these nested sums. So the first guy is 1, the second is this nested sum, and then the last guy, and then the other guys are obtained by this recursion relation. Was m minus 1 and divided by 4 squared. Okay, so the point of this formula is that it fixes all the coefficients, but it also gives us some structure which we will use when we want to study the subleading corrections. So we will write things in terms of these multi-zeta values, in terms of these nested sums. And so let me mention here a paper by Vasco. So we wrote the formula for all the OP coefficients, but Vasco also already knew the OP coefficients for the leading and then for the subleading Hessian trajectories from the flat space limit. And he also understood this connection with the Konishi operators, so this paper was really useful for us, and he explained this to us, so we are thankful to him. Good. So, what else I want to say? I want to say that these stringy corrections have some analytic structure. Analytic structure.
What is delta?
Delta.
The argument of Fm. Whatever.
That's the good point. So these F0s, how to put it, these operators, they depend on quantum numbers like spin, and another quantum number is delta, which comes to twist. And so the coefficients depend on delta.
So what's that other quantum number again? It's the twist?
Delta. So the quantum numbers are delta and spin. So that with delta and spin, this characterizes your operator.
But the twist is what? It's given by this formula plus delta, something like this.
And I think you should not write there, right?
Ah, sorry. So the twist is 2 square root of delta. I claim, given delta and L, the data of the operators is the delta. Now let me exemplify this claim. The twist is 2 square root of delta, that determines the twist. And the OP coefficient is given by this formula, which depends on delta and L.
How does this relate to the formula that you have on the right? That tau is tau 0, lambda a quarter. How does this?
I didn't write the dependence on delta and L.
So it's 2 square root of delta lambda to the 1/4.
That's right.
So
That's the twist.
Tau 0 depends. Tau 0 is this 2 square.
Yes.
Let me write it again. Tau 0 is equal to this.
Lambda to the 1/4.
And delta just labels the trajectory. This is how I should think about it.
And labels
Delta. Delta is an index.
does not label the trajectories. It's a good question, it does not label the trajectories. What labels the trajectory is n. So I need to write 2 formulas. So one formula is, so tau 0 is 2 square root of delta. And this can be written as 2 square root. And then you can have 1, now let me get this right. And n, and then you can have L over 2. And this n will label the trajectories. Take it as round, take n equals 0, n equals 0 equals, okay, this is the right one.
It's just a question whether you count trajectories from the bottom or from the top.
Same?
It's a question whether you label trajectories from the bottom, the lowest dimension for given spin, or the top, or your picture, or
This n is just the this n is just the usual way. So n equals 0 is the leading tangent trajectory. So given a spin is the guy with the smallest dimensions.
And in the work of Gapsar, Klebanov and Polyakov, it's just the string level number. That's what they introduced, little n. But from this perspective, we just see that the twist has to be 2 square root of some integer number at leading order, and we call that integer number delta.
Yeah, let me mention something which we think is cool. So, suppose consider one general string correction like this, and I wrote in here psi AB multiplied by sigma to the power A, sigma 3 to the power B. And we can set up an equation for this psi AB. The equation we set up is psi AB is equal to sum A B psi B A dot and so on. And then the equation that we established is this equation. So sum.
Is that alpha?
See?
So sorry, what is that?
This is psi. So just denotes some general stringy correction. I called it psi.
So should I think of psi as alpha plus beta over square root lambda and so on, the full thing? Or?
You can no. You should think of it as psi can be alpha or beta or gamma or delta. All right, and so it turns out that this psi AB vanishes for A equals minus B all the way to minus 1. And this is a non-trivial equation on the OP coefficient, which follows just from Bootstrap. So we think that this is a good equation. This is an interesting equation. So let me explain to you. So consider a general stringy correction, which is this one. In principle, A and B are just defined for when they are positive and non-negative. Okay? So A and B can be 0, 1, 2, etc. We write down this equation for psi AB. So we write down this series. And in this series, this P is a polynomial in A. And when you take delta large, it grows logarithmically in delta. And delta appears here, and this R is some integer that is picked such that this happens. Is this equation clear in my handwriting? This is a polynomial in A, and also depends on delta, and on the bottom we have delta to power, which is an integer, plus 2A. Okay? So we can derive 2 conclusions from this. First, as Mark was saying, you take A large, this series converges, so it defines for you an analytic function in A. So then we can take A commons. Step 1. Step 2, the following happens. You can write dispersive sum rules where the right hand side still converges and appears. So for Q equals 0, 1, 2, the right hand side will appear and it will converge, but it would correspond to having A negative. But having A negative is not something that can appear in the sum rules because it corresponds to having sigma 2 to some negative power. So if you look at this sum, further, you look at the dispersion relations long enough, and you write them for k equals 0, 1, 2, 3, etc., you will be convinced of this formula that psi AB vanishes when a equals minus b all the way to minus 1. By psi AB, I mean this sum. So these are pure bootstrap conditions on the OP coefficients, on the OP coefficients and twists of these Konishi operators. So the bootstrap tells you not just how to relate this data, the data of the string corrections to the data of the operators, it also gives you non-trivial equations for these operators. And we think these equations are very interesting. So for example, if I put b equals 1000, I'm telling you that this function should have 1000 zeros. So this should be interesting for bootstrapping the theory.
Perhaps one should say that for the coefficients alpha that appear in the Virasoro-Shapiro amplitude, Sagir also noted that these things could be analytically continued to negative values of this A and show that that was 0. And what we are saying is that this is true for all the AdS corrections to flat space as well.
So I have like 5 minutes, right?
Yeah.
So I will discuss quickly some corrections to the Virasoro-Shapiro amplitude, and then I will just mention some open problems, and then that's it. Okay, so in this talk we studied the alphas very carefully, but what we would like would be to study corrections to flat space. And turns out that the equations by themselves are super constrained. So even we know the left hand side, we know the right hand side, the fact that they need to be equal is a non-trivial statement. So what we can do is the following. So up until now our talk was very rigorous, now it's not going to be so rigorous, so we're going to start making guesses. And I'm going to make a guess for this beta. And so this will be our guess. It will be a guess in terms of 4 parameters. So I will guess this beta in terms of these zeta functions. This is I1, I2 from 0 to a minus 1. And this I1 plus I2 equals to a minus 1. And we get zeta and 3 plus 3 I1. I1, I2 equals 0. I just have to write the function. I1 plus I2. Zeta 3 plus 2. So the guess is in terms of these kappas. So I'm telling you that we don't know the kappas, but we guess that it has this form. Why do we guess it has this form? These betas appear close. This particular beta that I'm writing always appears next to some alpha, and this alpha has a similar form. So, in any sort of superunion, there's this principle of maximum transcendentality. So when you have these functions, the weight is given by the sum of these arguments. So the weight is given by the ordering number in which it appears. So our guess respects that. And turns out that this beta always appears next to an alpha, which is the product of 2 zetas. And so now we say, well, our beta is also a product of 2 zetas. It's not a product of 4 zetas. This is just a guess, but it is an educated guess. And so it is in terms of 4 parameters. So the equations themselves tell you that fix you 3 parameters, and then there's another parameter that you need to fix. You will need some input from integrability. The input is the following: that tau 2 at delta equals 1, delta equals 1 is equal to 2. So we'll need this input. Given this input, we fix all 4 parameters. Good things about this guess. Then there are 2 checks from localization. Well, localization tells you some betas, and then our guess respects this check, this fact. So that's a good thing. And our guess also tells you the following value for the OP coefficient in the Konishi operator at ascending order. So it tells you this, that this F2 is some number, which I will write now. Zeta 3. Good. So, any question about this? If not, I'll just discuss open problems and we finish.
Can I ask something about the thing you said before, this CAB?
CAB. This CAB.
Yeah, exactly. So there was a paper a while ago by Sinia, Gopakuma and Zayed, where they were studying this crossing symmetric transformation in
They don't say
space.
this. They do not say this.
It was, but it sounds related though, because they were expanding, handling some powers of.
You are right. It's not related.
Sounds.
When we wrote it, we didn't know about this paper, and they don't say this. This is very important. So the function does not have infinite zeros.
Oh, okay.
It has 10 zeros or whatever.
But is it related at all, or is it just?
It's related. No. They are thinking about meowing, so it's the same thing.
Okay.
Just okay, we were careful with this. This bound is really important. Okay, good. So I'll now discuss some way forward. So now we establish these equations. What we would really like to do is to solve them. How do we solve them? There are 3 paths, according to what I think. So one path, so as we saw, the bootstrap does not just establish the equations. It tells you way more. So we would like to understand that. We would like to understand how to solve these equations. We have some motivation for this because in flat space, people first discovered these string amplitudes from bootstrap. So first they discovered them from bootstrap, and they were thinking about linear trajectories, and so they came up with these gamma functions. We should do the same thing in AdS. So it seems to me that there should be a bootstrap argument that determines these alphas. Presumably it's from solving those xi's, and those equations look super nice. And once we understand how to obtain the alphas from bootstrap, this is going to be good because then it will tell us, should be illuminating on, well, to tell us something about how to get the betas and so on. So that's one thing, that's one path forward. Another path forward is people from integrability suddenly give us a bunch of data, and we're very happy, we fixed more numbers. Another path forward is, presumably, all these unique corrections would come from the worldsheet, so would come from a 2-dimensional integral. There should be an interplay, but we have no idea how to implement this in practice. But this should be good, something to explore. Okay, so this is how we move forward in this problem. Let me tell you some other problems that are similar and that I think are also interesting. So in this theory, there are operators that have large spin and whose dimension grows with the square root of lambda. Delta is equal to square root of lambda log L. To my knowledge, people have not studied them with the bootstrap. People have studied these operators at coupling and they have understood this log L, but they have not studied them with the bootstrap at strong coupling to my knowledge. I suspect, well, in here with the dispersion relation, you could access the UV, so it would be very good if we could do the same thing for these operators. But the dispersion relation cannot be the same, we'll need to play some tricks. Another thing, these operators are degenerate. Well, no, well, we expect them, these operators. Makes sense that these operators are degenerate, and that there are more quantum numbers to discover. So we should study mixed correlators, so O2, O2, OP, OP, should be the same. And finally, we can do this in other theories like ABGM. Good, so let's finish here.
Questions?
What's the exact signature of degeneracy in the subleading Regge trajectories, or is there a signature at all?
So in here we said that there are 2 quantum numbers, delta and L. Could be, because we were studying these operators, that leading order in the coupling. Could be that as you go to subleading order, then we discover that there are more quantum numbers. So for example, we don't want to assume that tau squared is the tau that we compute squared, because it would be a sum of tau I, tau I. Please.
In this large spin limit, like strong coupling, aren't the excitation like scalar fields on the long stretch string and it can move in the psi direction? But these modes are always massless, so it's basically like a continuum more than.
Okay, so you're saying this is impossible.
I'm skeptical. It's hard to resolve continuum on this sort of thing. Like you have lots of quantum numbers, not just a few.
I am less educated than you. For me, it's easy.
Yeah, I think that's correct.
That makes sense.
What we can say is that here we expect their contribution to be exponentially suppressed for large lambda, and I think it will be very hard to study. But perhaps what you can study are non-perturbative corrections to all these asymptotic series.
Yeah, I mean, I look forward to be proved wrong.
Yeah, but I think you're right.
Can you explain again the physical meaning of this box formula in flat space?
The physical meaning in flat space.
Or the logic behind this formula, but maybe in flat space. Flat space will be enough.
In flat space, you can derive exactly the same thing. Or let me just tell you the procedure of deriving it. So you would write a dispersive sum rule, and you would set up these equations in flat space. Okay? So step 1, you set up these equations. And then, but how to put it? you set this up, and then you're studying dispersion sum rule that depends on q equals 0, q equals 0, q equals 1, 2, etc. And when you do this, not all stringy corrections contribute. This is something that kind of goes through. So the way to think is that I can explain this more carefully to you afterwards. So if you consider q equals 0, 1, 2, etc., sometimes these guys do not appear because it would correspond to having a negative. However, this part still appears on the right hand side, which you can just compute and see, and so it vanishes. This is the logic. These are just some words. I will need to try to more carefully. But it's true.
And actually, for the Virasoro-Shapiro, it was just in flat space, it was some observation of Sagir done just like 2 years ago. So people hadn't realized that. So basically, the statement is that if you take the Virasoro-Shapiro amplitude and look at the coefficient in front of sigma 2 to the A, sigma 3 to the B, it is very hard to guess that actually, but if you are Sagir, you can, and he could guess that. And then some realization he did was that if you took A negative, that was magically 0, his formula for the right hand side.
Is that a statement of Virasoro-Shapiro, or is it a general crossing relation that's true for like some kind of Northern thing that's valid for any spectrum?
It's both.
For us, it's both. But at that point, Sagir just studied Virasoro-Shapiro without caring about anything. Sorry, Sagir and a collaborator, which is as important as Sagir. But sorry, I forgot.
We met. Okay, good. There are no other questions. Shall we finish?